Yes, well, that spreadsheet idea I've implemented with a spreadsheet, and it seems to give something like a false positive. Let me review what I'm talking about here. I made a spreadsheet and attempted a document for the spreadsheet. Here is the spreadsheet. The idea of this, see if I can, well, the idea of this is to determine an x such that when you add x to an n, these being the n's over here, you will get a number which is not divisible by 2 or 3. So n, the starting point, can be or not be divisible by 2 and 3 in 4 combinations. So these combinations are given by 0, 1, 2, 3, the 4 cases. So let's start with something like 5. 5 is mod 1 is 1 mod 2, and it's 2 mod 3. Hence, it's not divisible by 2 or 3, and that's case 1. In such a case, x is 0, and you get 2 numbers, 2 primes, 5 and 5, that are symmetric with your n. Okay, and 6, this would be one where it's both divisible by 2 and divisible by 3. I guess we call that the 0 case. I'm sorry, the 0 case, in which case you add 1 to both. That'll make the 6 turn odd, and it'll make it turn into 1 mod 3. And when you add 1, you get 5 and 7, 2 primes. Okay, that'd be another case. Okay, and when it's, I think we've covered that one, another prime, not divisible by 2 or 3, you add and subtract 0. And here's another example when it's divisible by 2 but not by 3. When you add 3 to that, you go to a 1 mod 2, an even plus an odd takes it to an odd, giving you 1 mod 2. And when you add 3, your 2 mod 3 stays non-zero. You add 2 plus 3 is 5, which goes to 2 mod 3. And when you add that, you get 5 and 11, 2 primes. So 3 works for that. I think, I've done all the cases, here's another case. So that's one more case. When it's odd, 9 is odd, but it is divisible by 3. Then you add 2, 2 being the modulus operator there. A odd plus 2 stays an odd, and when you add 2 to a 0 mod 3, it goes to 2, and that becomes not 0 mod 3. So adding 2 will get you out of those, and it returns 7 and 11, 2 primes. So it appears, based on this very sparse data set that we can find an x such that any n can be converted to something not divisible by 2 or 3, and we can get a symmetric values above and below that given n, which will be primes. Okay, using the get rid by adding and subtracting something that for sure gets rid of non-divisibility by 2 and 3. 11, another prime, this goes on. These things repeat, and the coloration suggests they're periodic, and also the numbers seem to be generally working up until you hit larger numbers past 25, which is 5 squared, which 5 squared would not be discriminatory in terms of being divisible by 2 and 3. It isn't divisible by 2 or 3, but it's not a prime. So to get 2 primes, I have to use something that's not in those case files, so to speak, adding 0, 1, 2, 3. Now I add 6, however, and I get 2 primes. Okay, this would be a 0 case. It's not divisible by either, but I need to add and subtract 6 quite a bit to get to 2 primes. But 28, I add 9, and I do get 2 primes. I had the initial idea that this was something of a solution, that I could prove that given any n, using its divisibility by 2 and 3, I could generate an x which would take that off for sure, and if I kept on adding these x's, eventually they would go to the symmetrical not divisible by 2 and 3's, and all primes are such that they're not divisible by 2 or 3. Doesn't go the other way. All call them 2, 3 primes, not divisible by 2 or 3. Call those primes of a certain type, 2, 3. Not all of those are regular primes. They can be, as we saw with 25, not divisible by 2 or 3, and hence a 2, 3 prime, but divisible by 5, and hence not a prime. Does symmetry of 2, 3 primes imply general symmetry to all primes? Eventually. And, studying this thing a little bit further, you do find that as you go along here, you can, here's 46, which is kind of a dramatic one. I have to keep on adding to 15 before I get 2 primes, but I do get 2 primes. I attempted incorrectly to make this into a paper, which, where is that? Which eventually, didn't work. I did, I think, do a correct lemma 1 here. For every n greater than or equal to 5, there exists an x such that n plus x and n minus x are not divisible by 2 or 3. And I do the cases there, and then I do display here of the idea. All regular primes are 2, 3 primes, but not all 2, 3 primes are regular primes. That's kind of obvious. By using various x values for any n, eventually a regular prime pair will be generated. And that one turns out to be not dependent on the previous lemmas. I think it is true, but it's not true because of the previous lemma. All right, so, yeah, darn. I think, that, what you'd hope is that you find 5 primes are symmetric, and you can start with 2, 3 primes and filter those without all numbers divisible by 5, and they remain symmetric. Remember the columns in those Goldbach tables, counting up to n, and then from n to 2n, those jobs, the columns, I'll swear in a stack of Bibles that eventually you get 2 primes in those, and that's your solution. But to prove that, you need the existence of an x, so that for any n, you get a Goldbach cell, a column with 2 primes. Right, so if I could continue with this reasoning and do an induction, that you start with 2, 3, and through 25 or 23, some number, and that's the square root property. If it's not divisible, if want to do the divisibility by n by primes, check the square root of n and do the primes less than that. So 25 square root is 5, primes less than 5 are 2 or 3. 2 or 3, if they're not divisible, you have a prime. So you do that, you get symmetry, you get to find an x per some rules, they'll get you your 2 primes. So it works for those tables through 25. Then you would like to go from 25 to 49 or something like that, and say now we add 5 to this, and they maintain their symmetry, and so forth. 49, and then after 7 is a whopping 11, 121. Keep on adding these primes, and they cover larger blocks symmetrically, guaranteeing an x. The rule-based thing, I had an idea, I think I put it in one of these videos, that you have rules like I did for 2 or 3. You had 1, you had 2, you had 3, or your x is one of those values. And it's per the case study. Versus, I think, what works, or is easier for sure, is you're guaranteed is eventually, as you change x, as you increment x, you'll get 2 primes for any n. And you prove that by an induction using a growing set of primes. 2, 3 was the beginning, 2, 3, 5, 2, 3, 5, 7. In a certain duration, a certain set of natural numbers. These primes, this set, they're symmetric. These x's, you have a max x, I think would be the idea, and they will generate primes. And getting a k-case to apply, 2, 3 by rote works. By plugging it into a spreadsheet, it works. And then if you do 5, and show that that works, can you then make an inference lemmas that'll say for the general case, k plus 1, or for the k plus 1 case, it'll work using the previous, before k cases for strong induction. It doesn't seem to be apparent that it's going to work. Could you say that using the 2 and 3 case, if I can, go to a spreadsheet and I keep on plugging in x, we'll do one more dramatic thing and then we'll get back to our regularly scheduled program here. I had something else I wanted to do. So down here, as I continue down this spreadsheet, I put x where I find an x that works. So I have it through 61. Now I hit 62. You see they're all 3s. That was just a copy and paste. So I'm going to change the x value. I'm currently at 59 and 65. 65 is not a prime. So the question is, can I change x to make this, to get 2 primes? Okay, so here it's a drum roll for 62. I'll start with 1. I get 1 in 63. 1 doesn't count. 63 is also divisible by 7 and 9. Try 2. Definitely not. Try 3. I did that one before. 5. 57 is divisible by 3. 5 plus 7 is 12, divisible by 3. 6, both even. 7, 11 and 3. 8, both even. At some point I could maybe infer. 9 and 71, 3 and prime. 10, 52, 11, 11 and 73, bingo. Okay, some will be easier than others. Like down here, 63, 1, 2, 3, 4, 59 and 67, bingo. 59, I'm pretty sure that's a prime. 67, we're done. So it seems like this works. Of course, this is, if this doesn't work, Goldbach has just proven, it is the case that, is that true? You get asymmetric. Well, at any rate, I think that's pertinent. I'll go that far. And I think it's true. I think I could keep on putting on x's and I will get, you see the problem. I get 1 prime, not another prime there. Both, I know, sometimes, I think I know, that they're both not divisible. I guess that's not right. By 2 and 3. So I'm not going to just the blue ones, which is somewhat more interesting. I just go to the blue, both 2, 3 primes, and then next 2, 3 primes, next 2, 3 primes. Within those, you would think that they would cycle where one might be divisible by 5 and not the other, and then arrange if they're both not divisible by 5, then they're primes. They're not divisible by 2, 3, or 5, like I said, in I think the 25 to 49 range, the square root of 50 being 7, say, and things less than that are 2, 3, 5, primes less than that are 2, 3, 5. If those are such that your n is not divisible by any of those, then it's a prime. So you stay with the blues. the blues are symmetric, eventually, do you get it's not divisible by 2, 3, or 5, either one. And is that for certain? You'd think that these would cycle, that not divisible by 2 or 3, and these are all the ones that are not divisible by 2 or 3. So all the ones that are not divisible by 2 or 3, and eventually it hits, a good zone where the periodicity of 5, and you're looking for 1, 2, 3, 4 mod 5s, you have 4 of those versus the 0. So just from probabilistically, you would seem to start hitting 1, 2, 3, 4 mod 5s with these. And so both of them hit and you're good. A proof of that. And then, given you can prove that, then it goes from there. Well, then you do 7 and so forth, and then I guess you're home. If 3 could imply 5, is that strong enough? The same argument holds for 7. They're going to cycle through all the ones that not divisible by 5. You get a bunch of those, and then like a sieve, eventually not divisible by 2, 3, 5, 7, both below and above. And for a range of numbers, that means they're primes. It seems, maybe. It seems like someone would have done that. But that said, there's a chance that I'm adept enough, quirky enough, that I'm, the table guru, and I just like making these tables and studying them, like eating candy, finding symmetries, of various types, and using those to make a table of this type. Table 1 that finds the solution, table 2 that finds the primes, and combine those, and you can find the primes. The other thing looming here is that you need a way to find primes, I think, that's built in. How do you know you have found the primes? I take that back. I think you can do a theoretical proof. Note the difference between I have a rule for finding x, given in n, such that I get n plus x is a prime, n minus x is a prime, versus I know an x exists eventually, somewhere out there. As to what it is, I don't know. And then the same deal goes to I don't know what the primes are, versus I know what the x is and I know what the primes are, the most robust information versus, you call it practical information versus theoretical. There's some x that'll generate 2 primes. I don't know the x, I don't know the primes. And I don't know the n that's going in. Other than, as I say, I think it has to be in a range, of n values will work with these primes. Does that imply I have to know the primes? I think it all goes to theoretical. Theoretical is easier to deal with. Making up cases is probably the worst. They go astronomical. All the possible 7 mod values, 5 mod values, and all of that, on and on and on. Okay, I had one more thing that I think is kind of interesting.